Welcome to this lesson on the exponential distribution. Imagine you're standing at a bus stop, waiting for a bus that arrives randomly but at a steady average rate. You might wait 1 minute or you might wait 20 minutes. How do we mathematically model this waiting time? That is exactly what the exponential distribution does. It is a powerful tool used to predict everything from how long a light bulb will last to when a radioactive atom will decay. Let us dive in and see how it works. To truly understand the exponential distribution, we must first understand what it measures. Unlike counting whole numbers of events, waiting time is measured on a continuous scale. It can be any decimal value. This distribution is explicitly linked to the Poisson process. Remember that a Poisson process counts how many events happen in a fixed amount of time, like 5 customers arriving in 1 hour. The exponential distribution is the other side of that exact same coin. While Poisson asks how many events happen, the exponential distribution asks how much time passes before the very next event. If customers arrive at a constant average rate, the waiting time between them is exponentially distributed. Now that we know what this distribution represents, let us look at its mathematical engine, the probability density function, or PDF. This formula gives us the relative likelihood of different waiting times. The symbol lambda represents the rate parameter, which is the average number of events per unit of time. The variable x is our actual waiting time. Because x is in the exponent and multiplied by a negative lambda, as the waiting time x increases, the overall probability drops towards 0. Physically, this perfectly matches our intuition. Shorter waiting times are highly likely, but the chance of waiting an incredibly long time gets smaller and smaller the longer you wait. This formula we just saw leads us to an important practical question. The probability density function only tells us the height of the curve at one specific instant. But in the real world, we rarely ask for the probability of waiting exactly 3.000 minutes. Instead, we want to know the probability that the waiting time is less than or equal to a specific value. To find this, we need to calculate the total area under the PDF curve from 0 up to our target time. This accumulated area is called the cumulative distribution function, or CDF. Let us look at the formula for the CDF next. Here is the cumulative distribution function. This formula is incredibly powerful because it instantly gives us the exact probability that the waiting time is less than or equal to our target time, x. Conceptually, it represents the accumulated area under the probability curve. Notice that as the waiting time x gets infinitely large, the term e to the negative lambda x approaches 0. This means the total probability approaches 1, mathematically guaranteeing that the event will happen eventually. If the rate lambda increases, the probability approaches 1 even faster, meaning you are likely to wait less time. Before we move on to how the CDF is derived, let us see this formula in action with a concrete example. Imagine a small coffee shop that sees customers arrive at an average rate of 4 customers per hour. The shopkeeper is waiting for the next person. What is the probability that they will wait less than 30 minutes? First, we identify our given values. The rate, lambda, is 4 per hour. Because our rate is in hours, it is absolutely crucial that we convert our target time into hours as well. So 30 minutes becomes 0.5 hours. We choose the CDF because we want a cumulative probability within a time frame. Continuing with our calculation, we substitute our rate of 4 and our time of 0.5 into the cumulative distribution function. Multiplying 4 by 0.5 gives us -2 in the exponent. This number actually represents the expected number of arrivals in that half-hour window. We calculate e to the power of -2 to be approximately 0.1353. Subtracting this from 1 gives our final answer, 0.8647.
Physically, this means there is an 86.47% chance that the shopkeeper will see the next customer within 30 minutes. Given the high arrival rate, this high probability makes perfect real-world sense.
Now that we have successfully used the cumulative distribution function to solve a real problem, let us understand exactly where this formula comes from. In calculus, finding the accumulated area under a curve means we need to integrate the probability density function. We set up our definite integral starting from time 0, sweeping all the way up to our specific cutoff time, x. We use a dummy variable t inside the integral to represent the time axis as we move along it. The integral sign simply means we are continuously adding up all the tiny, infinitely thin slices of probability under the curve. This continuous addition is the exact mathematical equivalent of summing up discrete probabilities, adapted for a smooth timeline. Moving forward with our derivation, we need to evaluate this integral. We take the antiderivative of our function with respect to t. When we do this, the constant lambda in front of the expression perfectly cancels out with the negative lambda that comes down from the derivative of the exponent. This mathematical cancellation is quite elegant and leaves us with a much simpler expression, negative e to the power of negative lambda t. Following the fundamental theorem of calculus, we place this resulting expression in brackets. Our next step will be to evaluate this expression at our upper limit x and then subtract the value evaluated at our lower limit 0. In this final step of our derivation, we plug in our limits of integration. First, we substitute the upper limit x into our expression, giving us negative e to the negative lambda x. Then, we subtract the expression evaluated at the lower limit, 0. This gives us minus negative e to the power of 0. Since any non-zero number to the power of 0 is exactly 1, that second term simplifies beautifully to a positive one. Rearranging the terms, we arrive at our final result, 1 minus e to the negative lambda x. We have successfully proven the formula for the cumulative distribution function, showing exactly how the area under the probability curve is calculated. Let us take a moment to visualize everything we have discussed so far. On the left, you are looking at the probability density function. Notice how the curves start high on the vertical axis and smoothly decay towards 0 as time increases. The green curve with the highest rate lambda drops the fastest. On the right, we see the cumulative distribution function. These curves represent the accumulated area from the left graph. They all start at 0 and rise upwards, eventually flattening out as they approach the horizontal asymptote at 1. This visually proves that as time goes on, the total probability of the event occurring approaches 100%. Shifting our focus, let us introduce another powerful mathematical tool, the moment generating function, or MGF. Think of the MGF as a mathematical DNA sequence for a probability distribution. It encodes all the important characteristics, such as the mean and the variance, into a single compact function. For the exponential distribution, integrating e to the power of tx multiplied by our PDF gives us this formula, lambda divided by lambda minus t. The variable t is simply a mathematical placeholder used to generate these moments. If we take the first derivative of this function with respect to t and plug in 0, we find that the expected waiting time, or the mean, is exactly 1 divided by lambda. Now we arrive at the most fascinating characteristic of the exponential distribution, the memoryless property. It is highly beneficial to contrast this with the discrete geometric distribution, which counts whole coin flips until a success. The exponential distribution is the exact continuous analog of that concept. Being memoryless means that the system literally does not remember how long you have already been waiting. If you have been waiting 10 minutes for a bus, the probability of waiting 5 more minutes is exactly the same as if you had just arrived at the bus stop right now. The past history is completely erased, and the past does not affect the future. Because of the memory-less property, we often need to calculate the probability that an item survives past a certain time, rather than failing before it. While the CDF gives the probability of failing before time x, the complement of the CDF gives the probability of surviving longer than time x. This is called the survival function, and it is simply e to the power of negative lambda x. Conceptually, it represents the remaining area under the tail of the probability curve. If the rate lambda increases, meaning failures happen more often, this survival probability shrinks rapidly. We use this formula because it is much faster than calculating the full CDF and subtracting it from 1. Let us apply the memory-less property and the survival function to a real-world engineering problem. An electronic component has an average failure rate of 0.1 failures per year. We are told the component has already been functioning perfectly for 5 years. We want to know the probability that it will survive for at least another 3 years. This problem directly tests the memory-less property. The vertical bar in our equation represents conditional probability. Because the distribution is memory-less, the fact that it already survived 5 years is completely irrelevant. The probability simplifies entirely to just the probability of surviving more than 3 years from scratch. Continuing with our solution, we completely ignore the 5 years that have already passed. The formula only cares about the future time window we are analyzing, which is 3 years. We plug our rate parameter of 0.1 and our target survival time of 3 into the survival function. Multiplying these gives us e to the power of negative 0.3. Calculating this value gives us approximately 0.7408. Physically, this means there is a 74.08% chance that the component will last at least another 3 years. In reliability engineering, this means an old working part is statistically just as good as a brand new one. Before we conclude, it is important to understand why this mathematics matters in the real world. The exponential distribution is the fundamental building block of queuing theory, which is the mathematical study of waiting in lines. Every time you call a customer service center and are placed on hold, the company is using this exact distribution to predict your wait time and decide how many operators to hire. It is also heavily used in reliability engineering to model when machine parts will break down, allowing companies to plan maintenance and offer warranties. Without it, optimizing internet data routing or hospital emergency rooms would be impossible. We have covered a lot of ground today, so let us review the key takeaways. First, the exponential distribution is the ultimate mathematical model for continuous waiting times between random events. Second, it is directly linked to the Poisson process, translating the count of events into the time between those events using a single rate parameter, lambda. Third, we saw how the cumulative distribution function allows us to easily calculate the probability of an event happening within a specific time window. Finally, it features a magical memory-less property, where past waiting time does not influence the future. Mastering this unlocks your ability to analyze lifespans and system reliability in the real world. Great job today!